Welcome back. We are in week 7 of inverse methods in heat transfer. This week we'll continue from last week. And if you recollect, last week we looked at probability theory. Within that, we had looked at basic probability theory as well as Bayes' theorem and the idea of probability distributions. Now, what we will do this week is to combine these two ideas and come up with inverse methods that use probability theory. What you will see is that this inverse methods using probability ideas is actually a superset of our previous methods. One advantage that we will see is that they are not, so they are the same methods regardless of linearity of model. Okay. So this is one major advantage of probabilistic methods. That is, they are the same methods regardless of whether your underlying model is linear or non-linear. For example, if you remember, when we had linear regression versus when we had non-linear regression, we had to use entirely different methods and entirely different iterative techniques. Whereas, whether the model is linear like W0 plus W1x or non-linear like A into 1 minus e to the power minus bt, in both these cases, we will use exactly the same probability ideas. Okay. One other advantage is we can see that we can recover many of our earlier methods. For example, linear regression, weighted linear regression, and our regularization from a probability viewpoint. In fact, one of those, which is the first two, I'll be doing right within this video. So from a probability viewpoint, we'll be able to recover all these previous methods. A third advantage that you will see right now is that probability methods give more detailed estimates of parameters. Okay. What I mean by that is, instead of saying that thermal conductivity is 50 watt per meter Kelvin, it will say it lies between 45 to 55, which is a characteristic, a hallmark of probabilistic techniques. So these are the three primary reasons within this course that we will be looking at probabilistic techniques. The first being that they work regardless of the linearity of the model. You are able to recover all the earlier methods right from the probabilistic technique, and they also give more detailed estimates of the parameters that we are interested in solving in inverse problems. The only problem, so the disadvantage of probabilistic methods is that they are computationally expensive. So because of this computational expense, in many practical realms, it's not really possible to do a full-scale probabilistic model, though we will see some approximations of this. Now, in general, when we go to inverse methods or you go to the inverse methods literature, you will see that a lot of the inverse methods literature is actually written in probabilistic language. So that's one other reason for us to study these methods. Some of the initial notation might be slightly confusing. Hopefully, if you have gone through in detail last week's lectures, you will be able to access this a little bit more easily. Okay. So what we will do now is go back to our slab problem and formulate it as an inverse problem, but in the probabilistic language. So let's go ahead and do that. So if you recall, we were looking at this simple slab problem. Again, I'm repeating the same problem again and again, just so that you have some orienting case. We had made 6 thermocouple measurements, and we were asked to find out what is the heat flux which is coming in, okay, given that you have not really given boundary conditions, but we have just given some internal temperatures. Now, we handled this, as you remember, by doing a simple least square fit. Here are some couple of wrong guesses, so to speak. They are wrong, not really, but it's just that they look off even to our eye, and we somehow came up with minimizing the least squares. Now, what we are going to do over the next few minutes is try to rederive, why minimum of least square. Okay, so our fundamental question right now is going to be why least square? Is there some other way in which we can justify the fact that we are trying to minimize the square of the difference between our prediction, which was y hat, and the ground truth, which was y, or the experimental method? So this is what we did, and we want to justify this, and we'll see that we can actually justify this particular problem via probability theory. Okay, so what we are going to do is to make a series of assumptions about what is true about our experiment. Okay, so what we notice, of course, is that there are all these thermocouples which are sitting here, and they are all making measurements. Now, the first assumption that we are going to make about not just this problem, but any problem that we go ahead and solve, is that the errors in this problem are additive. I'll explain what that means. What we are assuming is that at the base of all this is some reality. So we see this is what is measured, but underlying it is some reality, which is our model of reality. But on top of it, we are adding an error. Okay, so there is an error on top of it. This is error or noise due to some factors that we either don't understand or we can't control. Okay, so we either can't control these errors or we are not able to understand where these errors came from. So the assumption here is at each point, okay, so at each measurement location, so we had 6 locations here. At all of these 6 locations, we have some error which is being added, which is why our prediction need not look exactly like what our measurements did. Okay, so we don't expect something that goes through here, because actually we are trying to find a model for this noise, and we are going to try to denoise so as to obtain some actual reality. Okay, so that is the model that we are trying to get to, and this is because this can't be done uniquely, is why we have a ill-post or an inverse problem. Okay. Now, we are going to make further assumptions about how this noise behaves. So the second assumption here is that the noise, the error, has 0 expectation. Okay. Another way to say it is error for each one of these epsilons. Remember this notation is 0. What does that mean? Okay, so again, physically you need to understand it. It doesn't mean that the sum of the errors here is simply 0. What it means is if I take multiple realizations, if I do multiple experiments, so let's say we have the slab. Okay, so we have the slab and I did one experiment and this was the measurement that I got. Okay, now I did another experiment, so I might get slightly different numbers. like 15.44, 14.62, etc., etc. So this is experiment one. This is the only experiment, by the way, which we have access to. But right now we are thinking about what reality is, because reality is not that whatever I measure is the truth, but whatever I measure is the truth plus some error. This error will vary. I mean, just like when you take a slab and you measure its length, you would see that sometimes you'll measure it a little bit less and sometimes you'll measure it a little bit more. So similarly, what we are assuming is that epsilon in our language from the last week is a random variable. The error is a random variable, and the error has zero expectation. Okay, that is, sometimes you will measure more than the actual temperature, and sometimes you will measure less than the actual temperature. And overall, over infinite experiments, you will get an average error to be zero, which is what is written here. That is, the expectation of the error is zero. Okay. The third assumption we are going to make is errors are distributed normally. Okay. So now that we have decided that the error is a random variable, we have to now make a guess about what its distribution is like. So for our case, I mean, this need not always be the case for a genuine experiments, but for our case, just like we did last time, we are going to assume that the error has a probability distribution. And that probability distribution is a Gaussian. Okay. Now, when you say Gaussian, you have to give two things. What is the expectation or mu of that Gaussian, and what is sigma of the Gaussian? So we are going to say epsilon I, that is error at the ith thermocouple, is distributed normally, so that we will say drawn from, remember, we had used this notation the last week. It's a normal distribution which has mean or expectation 0, and its variance is sigma square. Okay, so when I write 0 sigma, this means variance equals sigma square. So right now, at least in the beginning, we are assuming that each of these thermocouples is measuring error at a different variance. Now, what would that mean? What that means is this. Okay, so if I assume that this is the truth, this line here is the truth, the red line here, what I'm assuming is that each time I measure the temperature, I'm going to actually measure a Gaussian, or I'm going to select from a Gaussian around this. So the temperature I actually measure could be anywhere in this range. Okay. Now, as we know that the Gaussian has a low probability further and further away, the chance that your error will be this high, this is low probability. Chance that you lie, typically you will lie between +2 minus sigma. So this you can draw as a error bar, which you might have seen. So 95% of the times when I make these various experiments, that is, I keep on repeating this, taking the slab, taking a different error, etc. 95% of the times I will lie somewhere here. A few of the times you will go outside of this. Okay, so that is the assumption we are making. So that's a reasonable assumption. Now, notice that something interesting happens here. What happens here is that we actually account for, in this model, the fact that there is a variation. So we are actually accounting for the fact that we have measurements that go away. Remember, in the function approximation, we never talked about why is it going away. In the function approximation, we said, okay, my values are just farther away. You know, I guess what I'll do is I'll do the best I can and fit something that goes in between. That's not what we are doing here. We are actually giving a process we are giving in detail, not in much detail, but at least in a little bit more detail, a process which accounts for the fact that there is going to be variation from experiment to experiment and person to person, but you still want the parameters of this line. So that's the key here in the probabilistic approach, modeling the error itself as some probability distribution, and in our case, a Gaussian. So let's move further from here. So if we write this epsilon in detail, we know what the normal distribution is. So we can now write the PDF. I'm going to call it F. F corresponds to the PDF of the error at this point. Remember what it means. Physically, all it means is I'm finding out what the shape is. That is, if I randomly pick something and say, okay, the error is so much, what is the probability that the error lies in this range or the error lies in this range? You can actually give a number by integrating this function. Okay. So you must again revert back to the previous week in case you do not understand what this means. Okay. So the Gaussian distribution here is 1 by square root 2 pi sigma I square e to the power minus epsilon I square divided by 2 sigma I square. Now, why is this epsilon I square? Because mu is 0. So it is simply a Gaussian. It is not a normal, what is called a univariate Gaussian. It's not N01, which we also say as the standard normal distribution, because sigma is not necessarily 1 in this case. Okay, now what does sigma represent? Okay, this of course represents the variance in the measurement of the ith, in our case, thermocouple. Okay, it could be anything else. Of course, the formulation is general. So the ith thermocouple that we have in our slab, each of them might be from different places. And when you statistically measure what happens, let's say you take 100 measurements each from here, you can actually do it inside the slab or outside the slab or wherever it is. You repeat those measurements. You will see each one of them might have a slightly different variance. If you recall earlier from this course, we did that data set also of p sizes, if you remember, and I had given that as an example of a weighted linear regression where each measurement had a different uncertainty. So now we are explicitly accounting for accuracy of the instrument. So in this case, basically, this is a measurement of the accuracy of the instrument. Typically, people use the term beta I equal to 1 over sigma I square, and beta I is called the precision. Okay, but I'll stick with sigma I for now. I also used lambda I a few times when I did weighted linear regression. Okay. So now we actually have errors. I can call this 3a because this is a direct consequence of 3. And the next key thing is that we are going to assume that all the measurements are uncorrelated. More importantly, I am going to make a stronger assumption. I am going to say, in fact, that they are independent. They are not just linearly uncorrelated, they are independent. Of course, if they are independent, this means covariance of epsilon 1, epsilon 2, all these variables, how many are, is 0. But remember, covariance is 0 does not mean independent, but independent does mean they are covariant. More strongly, since we have made these assumptions, 3 and 4 put together say that these measurements are what is called IID. IID would be independent and identically distributed. Strictly speaking, we can use this in two ways. We can say identically distributed, but with different sigmas. But generally identically distributed would mean that all sigma 1 is equal to sigma 2, all of it is the same and it's just a single sigma. Okay, so we can use this. For now, for this derivation, initially I will just assume different sigmas and we will see the special case where all the sigmas are the same. But the reason I use this term was for you to recollect this thing IID, which means independent and identically distributed. So the final assumption we are going to make, or the final two assumptions, in some sense slightly related assumptions, is all other parameters than the error. Well, the error is not a parameter, but everything else, the error of measurement other than that, are non-random. Okay, so for example, we are going to assume that the length of the slab is fixed. Length of the slab, the locations, x1, x2, all these are not random parameters. We actually know the locations. Obviously, when you make an actual measurement, these x1, x2, x3, x4, x5, x6, these are not actually fixed. There are errors there too. We can account for those as well. But all of it is in some sense put together and kept in this one single parameter, epsilon I. So let's just make that assumption. And one final thing, which is also related in some sense, like I said, is sigma I are known. Okay, this is not something I need to write explicitly, but let's assume that the variances are known somehow from details of the equipment. Okay, so details of the equipment. So when we say measurement error, that's not something that we are trying to figure out. That's something that's given to us. It's said that the thermocouple accuracy is so much and so on and so forth. Okay, so if we do all this, so what? Okay, so if I know all this, so what? So from here, we can show that we can actually recover least squares. I should not put an arrow here. I should actually put it here. From all these, least squares can be recovered as a natural consequence. What does that mean? Okay. We are going to see something called the maximum likelihood estimate, okay, which I'll explain shortly. And this is another way of handling inverse problems, or another way of looking at this base problem. So this is called MLE. Okay, so this maximum likelihood estimate. Okay, so let's see what we mean by maximum likelihood estimate. Let's look at these three lines. Okay, line 1, we'll call it L1, line 2, and line 3. Okay. Now, our original data was like this. We had some x1, x2, let me write this fully, x3, x4, x5, x6. We had some y data, y1, y2, y3, y6. And we want to figure out which one of these three lines is the best explanation. Which line? So this is the way we are going to pose the question. Is the best explanation of the observed data. Okay. Like we discussed right at the first week, this is somewhat like a detective problem. Okay, so let's say somebody goes, sees a murder, or doesn't see a murder, sees a dead body, and they look at all the clues which are around them. So this we treat as if they are clues. Okay. At x1, I saw y1. At x2, I saw y2. Now, I have different possibilities. Someone L1 could have killed, L2 could have killed, L3 could have killed. Now, if L1 killed, how well does all my observation fit the fact that L1 did it? If L2 generated this data, how well does all my data get explained by L2? And if L3 did it, how well does it explain it? Okay, so this is the way we are going to look at it. And here is where probability theory really helps. When we looked at least squares, we had like a very rough tool. We just said, okay, the gap between L1 and this data is too much. So maybe that's not so great. But that is still too crude. Whereas what we are going to ask is, which line is most probable? Okay, so please notice this word, most probable. We'll modify the meaning of this through some of the videos that we do. We will see different levels of the same idea. The first level is this very simple idea. I have already observed this data. This was the data that I showed you right at the beginning. I have already observed concrete numbers here. Which model best explains the data? Okay. So how do we write it in probabilistic language? We want to say, I observed, I am already given X. Okay. I want to maximize Y hat. Okay. The Y hat that fixes this X. Okay. For some given guesses. So given some line. Okay. So here is the observed data. Now each L will correspond to some Y hat. In fact, if you want, let me write it more clearly. I want to show this. I want to maximize. There are different lines for for all the given X's. All these lines, each of them have a different probability. I want to maximize that probability. So I'm going to write it in some technical term. So let us see how each one of these data points is generated for a given line. So the generation process will be like this. First, we are given some xi, yi. Okay. In our case, I goes from 1 to n, where n is 6. Now, I am going to choose some hypothesis line. Okay. This is very much like how we did gradient descent also. So this hypothesis line is chosen by choosing W0 and W1. Okay. So for example, I choose W0, W1, I get this line. I choose one W0, W1, I get this line, and some other one, I get this third line. Okay, so we choose that. Now, third step, this is the key step. Randomly assign some error to it. Okay, this is how each experiment takes place. Remember, we had initially modeled our entire process of generating this data as yi is y hat I plus epsilon I. So there is some truth, which is our line. And then this was just randomly assigned. This is how each experiment takes place. Okay, so you do this and you pick some error. And how do you pick this error? You pick this error by drawing from this distribution. Imagine this is like I said, this is just like a ball, or this is like a bag, and you're just drawing some ball from it, and it will give you a value of epsilon. How we do this in practice, we will discuss later this week. But this is the probabilistic process. So we are modeling reality as if it is doing this. Okay, so keep So evaluate the probability that we will observe the given data for the choice of parameters. In step 2. Okay. So this is the way it happens in practice. So we come here. Let me repeat this graph. Suppose I want to evaluate the probability that L3 explains this data. So this is the way I'll do it. I'll come here. Okay. I'll come to 1.1. And then I'll say line 1, right? Or sorry, yeah, line 1. So I'll come to line 1. Let's say it has the parameters, let's call it A1 and B1 instead of W0 and W1. This is easy. So line 1 then generates y hat equal to A1 plus B1x. All right. Now, once y hat is equal to A1 plus B1x, now I know what the probability of this point is. How do I evaluate it? We will now draw the probability distribution of epsilon 1. Epsilon 1 is a Gaussian which has mean 0, that is centered around right around line 1 and some given sigma. Now, all we need to do now is to evaluate the possibility that you will get this point here for that given epsilon. Similarly, I'll come to point 2 and I'll draw again the epsilon 2 distribution here, and I'll find out the possibility that this point will come. Similarly here, you will now see if I put it centered around line 1, this becomes very low probability. You see the tails as we saw in Gaussians. And if we come to this point, for example, again, epsilon is centered here. This is again very low probability. Now, since these events are independent, we can say that probability of observing the data given these locations for this parameters A1 and B1. Okay, so this language I'll explain once more. The probability of observing this is a product of the probability that the first point is observed, because these are independent. The first point is observed with the same parameters, multiplied by the probability that the second point is observed given these parameters, so on and so forth. So let me write this in a mathematical language. Okay, since the errors are independent, okay, we can write that probability that we will see the specific measurements we made, or actually the range of measurements if we want to say it a little bit more precisely, but this is actually just the PDF. So for observing the PDF for the given input data with some choice of parameters. So let's say we made some choice. Again, I'll use A and B maybe just for now, so that we don't get confused by the subscripts, is the product. So product we denote by pi, if you remember, just like sigma is for sum. The product over all 6 measurements or n measurements in general of, I should have called this Pyx, Pyi xi given a comma b. Okay. Now this PYIXI, if you remember, yi was y hat I plus epsilon I. So since only this portion is the random portion and this portion is fixed, the probability of yi given xi, I am not proving this, but you can imagine this with fairly straightforward thought process, is the same as giving the error. So once I give you a point, that is the basic model, and I give you an error, obviously you can predict what was measured. Okay, it's the same thing here. So all it says is the only random portion in our measurement is the fact that there was a random error. Okay, so this tells you that this value here is what we wrote earlier, 1 by square root 2 pi sigma I square e to the power minus epsilon I square by 2 sigma I square. Okay, so before we get lost in the symbols, all we are saying is this. If I want the probability or the probability distribution function at this point, given that the ground reality was this, then this point is going to have a very, very low PDF because it's far away from the mean. Okay, so from the mean here, which is just this line. Now, if on the other hand, I took this model, the L2 model, this point would become more probable. That is, the error required to reach this point is fairly low, whereas the error required to reach this point is fairly high. And we know that the error is normally distributed, so it can't be that high, or at least high errors are not that likely. If you keep on demanding from a data set that every point is coming because there was a lot of noise. Okay, so we can always explain saying, hey, your model is bad. Let's imagine you give this as the model of reality, or let's take this because this is less messy. L3 is the model of reality, and I want to explain these 6 points which are sitting here. I say, oh, why is your data so far away from reality? You say, because there was a lot of noise. At the same time, you also say that my instrument's accuracy is very high. Its variation is low. So then you'll say maybe your model itself is wrong. This is a much better model with low noise. This might be a decent model with high noise, but this is a much better model. Okay, let's come to this again. So this is for one data point, and this is for the whole data set. Why is that? Because if each data point has this error, then the whole data set, as I have written before, is product of individual data points, which turns out to be, in this case, product of 1 by square root 2 pi sigma I square e to the power minus epsilon I square by 2 sigma I square. Okay, but this still doesn't look like anything like d squares. Now here is where a trick is. So we take log of both sides. So you say log of p x, this product turns into a summation. So it becomes summation of 1 over 2 pi sigma I square I equal to 1 to 6. Okay. Plus summation of minus epsilon I square by 2 sigma I square I equal to 1 to 6. This is just by taking log. There should be a logarithm here. So I forgot to write that. Log here is ln. Okay, so that's what I'm saying. 1 by square root 2 pi sigma I square. You can make it minus, but it will shortly become irrelevant. Okay. Now, since a log is a monotonic function, if I am finding out which parameters maximize probability, This is the same as asking which parameters maximize log of probability. Okay, because if log is maximized, probability is also maximized. So this means we need to maximize this plus this. Now this is fixed. Y, of course, 2 pi is fixed. We have no control over it. And sigma is from the instrument. We can't do anything about it. So what you can do is you maximize sigma I equal to 1 to 6 of epsilon I square by 2 sigma I square. Now, since there is a negative here, we can say this is the same as minimizing epsilon I square by 2 sigma I square. Now, I'm going to make it 1 to n just for n points. But what is epsilon? Epsilon, remember, was y equal to y hat plus epsilon, which means epsilon is simply the error. Y hat minus y, or sorry, y minus y hat in our notation. Yi minus y hat I. So what we are saying is minimize sigma yi minus y hat I square by sigma I square 1 by 2 I equal to 1 to n or 1 to 6, let me say, to maximize the probability of y given x. Now this maximizing this y given x is called likelihood. What it means is how likely is y given x. How likely were you to observe this data set or these temperatures at these particular locations? That's what it physically means. Now notice this. For all sigmas being the same, this immediately gives us minimize 1 by 2 yi minus y hat I square. Of course, the sigma square is irrelevant. This is, of course, the least square loss function. That is performing least square is equivalent to maximum likelihood estimate. Okay, so you might get a little bit lost in the math, even though if you review it, the math is actually just 2 steps. Okay, so what it means is this. See, amongst all the infinite lines that could have fit this data, amongst all the infinite lines that could have fit this data, only one of them has the maximum probability given this data set. What that means is each of these lines has a certain probability that it explains this data. Okay, because when I keep the line here, it means this data has a probability, this data has a probability, this data has a probability. And I need to multiply all these 6 probabilities in order to get the probability that this line could have generated this data. Okay. Now, given all this, given all the infinite lines, there is one line which gives you maximum probability of explaining this data, of maximum likelihood of this data. Okay. Now, that line also happens to be the same line that minimizes these squares. So, therefore, minimizing the least square is equivalent to maximizing the likelihood. Now, what happened to this? This, if you recall, is exactly what we did for with this is weighted least squares. That is, if each of the points here had a different variance, that is, let us say there is a point with very high variance like this one, and that is only because the thermocouple was very noisy. In that case, the probability of this and the probability of this might actually be very, very close to each other, even though, or even this. If this is something which is highly accurate, you actually have to blow up the difference. And if this is less accurate, you have to actually reduce the difference. And as we discussed in weighted least squares, we need not weight each point the same because each point has a different variance. So from maximum likelihood, we are able to obtain both normal least squares as well as weighted least squares in one shot. Now, this, of course, was a little bit of theory, and it turns out this is not the only way, or this is not the end of how to use probability theory. In the next video, we will say that this is fine, but what if I already have an idea of what this line is supposed to look like? Okay, what if I have, in other words, a prior? Remember that prior example that we did in the COVID case in the last week that strongly affects what our final estimate is. So we will try to incorporate ideas. For example, you are estimating a thermal conductivity of a material. You would like to incorporate the idea that you already know that the material's thermal conductivity should look like the thermal conductivity of, let's say, steel. In that case, that should be incorporated into the actual information. And we will see how probability can do that and what the corresponding equivalent of what we already did is. So let's take a look at that in the next video. Thank you.